This video is about indeterminate forms and what's called L'Hopital's rule. Yes, it looks like Al Hospital's rule, but it's pronounced L'Hopital's rule. For our notes, we'll start with the definition and say the following forms are considered indeterminate. Now, several of these we've already seen in the context of calculus when doing limits, but some of them we have not quite yet. There are 7 of them. I'll list them out here one at a time. First, we have 0 times plus or minus infinity. Secondly, infinity minus infinity. Thirdly, 0 to the power of 0. Fourthly, infinity to the power of 0. Fifthly, 1 to the power of infinity. Sixthly, 0 over 0. And 7th, infinity over infinity. Now you'll notice those last 2 are familiar. We've already done limits in the context of calculus where we encountered those kinds of indeterminate forms, and we actually had ways to deal with them. There were many algebraic tricks we tried or did in order to kind of wiggle our way out of those indeterminate forms and work toward an answer. These other types, now these first 5 types that are listed here above those, are ones that we're going to see now more than we have before, though before it might have been possible to see one. Usually we rearranged it until it wasn't. It was one of the ones below. In fact, that's kind of where we're going now. L'Hopital's rule states this: suppose f and g are differentiable and g prime of x is not 0 on an open interval I that contains a, except possibly at a. If the limit as x approaches a of f of x over g of x equals 0 over 0 or plus or minus infinity over plus or minus infinity, by the way, also known as just infinity over infinity. Sometimes the plus or minus isn't always put in there, but it means the same thing here. Then the limit as x approaches a of f of x over g of x, which by the way is what we just started with here, then that limit is equal to the limit as x approaches a of, notice, f prime of x over g prime of x, as long as this limit exists. Okay, so what this is saying, what this theorem or definition is saying, is that if you have a limit which gives you one of these 2 indeterminate forms, 0 over 0 or infinity over infinity, then you can simply take the derivative of the numerator and the derivative of the denominator and then take the limit of that quotient and you'll get the same value ultimately. So this works, of course, sometimes when you have these indeterminate forms and you can't make your way out of them with methods we've already used. Okay, so now let's go back and actually refer to how this pertains to the indeterminate forms. Remember we grouped these indeterminate forms as in the first 5 and the last 2? Well, what this definition or theorem or rule is stating is that it only works when you have one of these last 2 indeterminate forms. So this is where L'Hopital's rule applies, which means if you have any of the first 5 indeterminate forms, your job is to do some algebraic kung fu or tricks to turn it into these last cases of indeterminate forms. So there can be a little algebra involved in that, but the point is you can only use L'Hopital's rule with these last 2 indeterminate forms. Now, just a little preference on a notation here I like to use for simplicity is that since L'Hopital's rule is spelled hospital, and the symbol for hospital that you would see like on the side of a road somewhere is a large capital H, I like to refer to L'Hopital's rule as a large capital H in a circle, just so that in my notes you'll know exactly when we're using it. There are some very important notes that are going to go along with this rule, and let's list those next. Note, this also works for when x is approaching a from the left or a from the right. Remember, x approaching a, that was the limit variable in our limit here. And so it works when you're approaching just one side of a limit, or it also works if x is approaching positive or negative infinity. So a doesn't have to be a real number, it actually could be infinity or negative infinity, and this rule still works. Secondly, let's note that this method should be used as a last resort after attempting other methods to find limits. If you go back to when we discussed limits at the beginning of our calculus course, we did them analytically with a huge series of outlined steps for tricks to use if you get an indeterminate form like this. And none of those steps included L'Hopital's rule. In fact, then when we were doing the limits, we said, you know what, we're going to hold off on L'Hopital's rule if you've seen it before. We're going to do it later. Well, this is it. This is later. But the reason we have to use this as a last resort is because sometimes it can actually give you a false result when one of those original methods for wiggling out of these indeterminate forms would actually be better and give you the true limit. Now that can seem a little concerning or disconcerting or ominous, but it's true, and that's why often students will try to use L'Hopital's rule too soon, thinking, oh, I know L'Hopital's rule, I'll just use that on this problem, when in fact it may not be the best method. So after considering all of our previously known methods for getting out of these indeterminate forms, if they are not promising, that's when we'll go ahead and use L'Hopital's rule. And thirdly, let's note that this is not the quotient rule for derivatives. When you go back and look at this definition, the conclusion of it is you're taking the limit of f prime of x over g prime of x. Okay, that's simply a quotient of derivatives. It's not the quotient rule. You're not taking the derivative of the quotient f over g. You're taking f prime and putting that over g prime. So there's an important distinction there as well. Let's try some examples where we want to find now limits and possibly need to use L'Hopital's rule. Our first example is the limit as t approaches 0 of a fraction expression where the numerator is 8 to the power of t and then minus 5 to the power of t, and that numerator is all over t. Now, upon using the old direct substitution or attempting it, if you plug in t as 0, you'd have 8 to the 0 minus 5 to the 0 in the numerator. Well, that's 0, right? 8 to the 0 is 1, so is 5 to the 0. 1 minus 1 is 0. But then if you plug in 0 for t in the denominator, you also get 0 there, which means we have 0 over 0. Okay, now again, in the old days when we started limits, we would try a series of different algebraic steps to get out of that problem. That's an indeterminate form. But none of those steps that we used then will actually work or apply in this case. There's no way to rationalize this, there's no way to factor this, there's no way to divide by the highest power of the denominator that will help. You can try all those steps in vain, they're not going to go anywhere useful. When we have a limit that gives us a 0 over 0 or infinity over infinity like this, and we're already intending to use L'Hopital's rule, that makes us happy. I'm going to put a smiley face there because we already have the indeterminate form we want. So let's go ahead and use L'Hopital's rule, and his rule would state that this limit now could be rewritten as the limit as t approaches 0 of, but now instead of putting our original expression or function, we're going to take the derivative of the numerator and the derivative of the denominator. So you look at the numerator and hopefully recall some of our derivative rules for exponential functions. When you have 8 to the t, the derivative of that term would turn into 8 to the t times the natural log of 8, okay, minus the second term being 5 to the t, that derivative would turn into 5 to the t times the natural log of 5. So again, that's kind of just going back and using some of the shortcut derivative rules for exponential functions. You may need to review that as necessary. If the denominator was just a t, the derivative of that would be just a 1 then. Well, at this point, after having taken those derivatives, remember L'Hopital's rule says that the original limit is now going to be equal to this new limit, which now uses the derivatives of each numerator and denominator of this function. And this next, this limit, now that we've found using the derivatives, could be found simply by direct substitution. 8 to the 0 is 1. So if I plug in t as 0, I'll have the natural log of 8 simply as that first term, and then for the second term, the natural log of 5. 5 to the t would be 5 to the 0, which is 1. So natural log of 8 minus natural log of 5 is how we can do direct substitution. Notice that's not indeterminate, that's a real number value. It's an ugly number, but we'll just leave it in exact form here with no decimals. So natural log of 8 minus natural log of 5 is how we can get this limit thanks to L'Hopital's rule. Let's try a second example. This one is the limit as x approaches infinity of the square root of x times e to the negative x over 2. Now notice that this is where x is approaching infinity, and if you were to try to plug infinity in with direct substitution, understanding that infinity is not a number here, this would turn into the square root of infinity, which is infinity, times e to the negative infinity would really be 1 over e to the infinity, which is actually 0 if you go back to some of our limit understandings of those kinds of algebraic expressions, which means upon a consideration of direct substitution, even just conceptually with infinity, we have infinity times 0, which is actually not good. That's going to make us a little sad here because that's not one of our L'Hopital rule derivatives, indeterminate forms. Furthermore, there's no other good algebraic trick we might be able to use to get this out of that scenario without going toward L'Hopital's rule. So what we're going to try to do is, first of all, rewrite this until we get one of L'Hopital's indeterminate forms. If I simply rewrite this as the limit as x approaches infinity of the square root of x over e to the x over 2, so now the e to the x over 2 is in the denominator, which corresponds to that negative exponent it had originally. So I'm not really even doing much algebra there. I'm just simply rewriting this exponential term down in the denominator since it had a negative exponent. In that case, if I were now to plug in infinity in a direct substitution conceptual kind of way, then notice the numerator would be infinity, and so would the denominator, which would give me infinity over infinity. Now that makes us happy because that's one of L'Hopital rule indeterminate forms. If that's the case, then I can use L'Hopital's rule on this limit and say this equals the limit as x approaches infinity. Remember we said in one of our notes that this L'Hopital's rule works when x is approaching infinity as well as a real number. In that case, I'm going to take the derivative of the numerator, and that will turn into 1 over 2 square root of x. The derivative of the square root of x is 1 over 2 root x. And then in the denominator, I'll take the derivative of e to the x over 2, which would become e to the x over 2 times 1/2. There's a little chain rule going on there. And now, if I simply try plugging in conceptually here infinity for x, I'll have 1 over infinity in the numerator, which is actually 0. And in the denominator, I would still have infinity, but given our understanding of infinity and its expression, 0 over infinity is defined as 0. It's not indeterminate. In fact, if you go up and look at all the options for indeterminate forms, you will not see 0 over infinity there. It's really common to get confused on, which forms are indeterminate and which are not when you're just kind of learning these indeterminate forms. So be sure to keep that list handy, read it several times as you're practicing to know which forms are and are not indeterminate. This one is determinable and it's just 0. Let's try a third example. This one is the limit as x approaches infinity of x to the 3/2 power times sine of 1 over x. Now again, if we try a direct substitution right away, we're going to end up with infinity for the x to the 3/2 power times, well, if you plug in infinity for the sine expression, 1 over infinity as the input for that sine would really be like a 0. So sine of 0 is 0, which means we really have infinity times 0 here, which makes us a little sad because that's not one of our L'Hopital forms. So what we want to do is find a way to wiggle out of that and get into a form that will work with L'Hopital's rule here. You could also go back and try any of the original methods we had for trying to get out of a limit like this, but none of them seem to work here. So we're going to try to get this into L'Hopital's rule first. And to do so, I'm going to try a trick where we're going to take this, rewrite the limit as x approaches infinity, and then we're going to split this power of x up. Okay, this is not obvious unless you've seen an example of it. Okay, so now you're seeing an example of it, which means hopefully now you'll be able to recognize it. But this can work as follows. I'm going to rewrite x to the 3/2 as x times x to the 1/2. So algebraically that would be equivalent, and I'm just simply rewriting that factor, x to the 3/2, as this product x times x to the 1/2. Then I'm just going to keep my sine of 1 over x as it was, kind of there on the end. Now this still doesn't quite fix the problem. In fact, it has not changed from the infinity times 0 that we just figured out we have, which means we're not good yet. So what we're going to do next is even a little more tricky. We're going to rewrite this as the limit as x approaches infinity of, now I'm going to kind of utilize or borrow one of our special limit forms. If you recall back when we did special limits, we could say the limit as x approaches 0 of sine of x over x is 1. That's one of our special limits from a while back when we were doing limits, and that limit could be utilized here, but it's not obvious even yet. What we're going to do is leave the sine in the numerator. So we have sine of 1 over x, but then I'm going to do some algebra here and make this over, so sine of 1 over x over 1 over x. Now you may say, well, how'd you do that? Well, remember, dividing by 1 over x is the same thing as multiplying by x, which means we've accounted for that x factor in that way. In fact, I'll just color coordinate how that happened. But notice we have not put in this x to the 1/2 power, so we can just kind of tack that on after our fraction that we've now put in here. Okay, so ultimately we've rewritten this limit to be the limit as x approaches infinity of sine of 1 over x over 1 over x times x to the 1/2 power. Now you've seen this kind of thing before. We can use a u substitution to say let u equal 1 over x, because really I would like to use the special limit that I have, and I don't have sine x over x, I have sine of 1 over x over 1 over x. So as you've seen before, we can do this little substitution. If I let u equal 1 over x, then importantly, as x approaches infinity, which by the way is what's happening in this problem, as x approaches infinity, we would have u approaching 0. 1 over infinity here would be 0. So that actually all locks together in line with this problem in a way that's usable, and with the bounds of the limit that we're trying to go for the special limit. But also notice that would kind of leave this extra factor at the end here in the dark, the x to the 1/2 that we have after our ratio involving sine. That factor wouldn't be playing along with this substitution unless we solve this substitution for x and then go ahead and replace it. So really x is 1 over u, which would mean that x to the 1/2 is really 1 over the square root of u. Okay, so that's taking the substitution we had originally, solving it for x, and then taking the square root of both sides will allow us to replace even this x to the 1/2. So now let's rewrite using what we have. We're going to say this is now the limit as u approaches 0, and actually it's not just approaching 0, it's approaching it from a positive direction. I'm going to say as u approaches 0 from the right, which is true of this. So if you take this function that we use for the substitution, 1 over x, recall the graph of 1 over x, has a couple branches on it. As x approaches infinity, we're kind of trailing off to the right side of it. This function is approaching 0, but it's kind of coming down on it, so it's approaching it from a positive value. That's going to matter because of this second factor we have to use in our limit here. So we're saying we now have the limit as u approaches 0 from the right of the sine of u over u times 1 over the square root of u, as we've already stated. Now we can start plugging stuff in. This is the special limit in the first factor, so that's really 1 times, and then 1 over the square root of u, as u approaches 0 from the right, that would turn into a positive infinity. You can verify that either by looking at a graph, or to recall that, or just by plugging in some values, getting close to 0 but in a positive direction. So we could say 1 times infinity, of course, is just infinity. That's not indeterminate. That is an actual value infinity there for that limit. Let's try a fourth example. This one is the limit as x approaches 0 of the quantity in parentheses here that we have is the cosecant of x minus the cotangent of x. Now if you try a direct sub on this by just plugging in 0, cosecant of 0, remember cosecant is 1 over sine, so sine of 0 is 0, which means we have 1 over 0 for cosecant of 0, minus cotangent of 0 would be the same thing, that'd be 1 over 0, cotangent is cosine over sine. So we have 1 over 0 minus 1 over 0, which, okay, you may be able to call that infinity minus infinity, but that's not quite one of our L'Hopital indeterminate forms, which means we need to do a little bit of algebraic work on this one. And so let's go ahead and see what we can do by rewriting this as the limit as x approaches 0 of, let's actually write out these trig functions in their more basic definitions. We've already mentioned it. Cosecant of x is really 1 over sine of x, minus cotangent of x is really cosine of x over sine of x. And in doing this, it doesn't change anything yet, but it might give us a hint that we actually have a common denominator already in the way that these are set up. So let's simply rewrite this as the limit as x approaches infinity of, I'm just going to write this as one fraction, so 1 minus cosine of x all over sine of x. But now, if I try direct substitution on this, in the numerator, 1 minus cosine of x when x is being plugged in as 0 would be 1 minus 1, which is 0. And in the denominator, sine of 0 would also be 0, which means now we're getting 0 over 0, which is actually good news. It's still indeterminate, but the reason it's good news is because that's one of L'Hopital's indeterminate forms. So let's now try using L'Hopital's rule, where we rewrite the limit as x approaches 0, but this time we take the derivative. Now notice I'm working on this previous step that we just wrote, because that's the step that came out with the L'Hopital indeterminate form 0 over 0. I'm not going back to any previous step and trying to apply L'Hopital's to it. Only the exact limit that we just got with this indeterminate form of 0 over 0. If I take the derivative of the numerator of this previous step, it was 1 minus cosine of x. The derivative of cosine is negative sine. The derivative of 1 is 0, which means that numerator's derivative is simply sine of x. They'd be like minus negative sine, so sine of x it is. And then in the denominator, we had sine of x. The derivative of that would be cosine of x. Okay, so ultimately now, after taking the derivative of the numerator and the denominator, our result is simply sine over cosine, and we're trying to take that limit as x approaches 0, which you can simply plug in. Sine of 0 is 0, cosine of 0 is 1, so what do you know, 0 over 1 is actually 0, which means we've now found the limit, thanks to L'Hopital's rule. Let's consider a fifth example. This one is the limit as x approaches 0 from the right of the following expression, 1 over x minus 1 over the tangent inverse of x. Or you could also write arctan, same thing as tangent inverse there. Now before we really get going with this example, I want to recall a couple important things that'll help us out, and that is the graphs of some of these functions. So if I have 1 over x That graph, as you may recall, has a couple branches in quadrants 1 and 3. Of course, it has vertical and horizontal asymptotes there on the x and y axis. Okay, and then also, if I have tangent inverse of x, that graph has two horizontal asymptotes, and then the function itself kind of snakes up through the origin, approaching the lower asymptote to the left and the upper one to the right. Of course, those are at pi over 2 and negative pi over 2. Those details will only serve us in this example. That's why I recall them. You don't really just need the graphs to do this, but I think they really help. And here's how. First of all, if you take a look at this limit, by trying direct substitution, we're approaching 0 from the right. And so for 1 over x, where this graph is, approaching 0 from the right, that would mean we have positive infinity. Now for the second term, the 1 over tangent inverse of x, this one's a little trickier. Now I wrote out the graph of tangent inverse, but this expression says 1 over tangent inverse. Well, here's why the graph is helpful. If you look at x approaching 0 from the right on tangent inverse, that means we're approaching it in from a positive direction. Of course, the limit there is 0, but 1 over 0 is some kind of infinity. If you go back to limits by deduction, we mentioned that this is plus or minus infinity. We just need to use some more information to know which of those it is. Well, in this case, when we're approaching 0 from the right, notice that this tangent inverse function is approaching, the values of it are approaching 0 from a positive or from above. That's what's happening here, which means we could call that a positive infinity. The reason that kind of detailed look at this matters is because if we had ended up with infinity plus infinity at this point, that would be just infinity. We'd be done. But this is now infinity minus infinity, which is actually sad because that's not one of L'Hopital's indeterminate forms, but it is indeterminate. Okay, just to clarify on this deduction thing, this step can be a little tricky here. When I have 1 over 0, if you imagine using deduction on a number line, we're approaching 0 from the right. And as we do, the whole point of this little expression, the 1 over tangent inverse of x, is that the numerator is 1. That's guaranteed to be positive. But then the denominator is also positive, and that's what we said by looking at the graph of tangent inverse there as x is approaching 0 from the right. And so positive over positive gives us a positive infinity. Now, of course, that positive infinity follows the negative sign in front of it. So really we have infinity minus infinity. Now, the reason these details matter is because we ended up here with infinity minus infinity. If we had not treated this second term carefully enough and thought, oh, that might be infinity plus infinity, well, infinity plus infinity is entirely a different answer. So in fact, infinity plus infinity is not indeterminate. That would just be infinity. Rather, infinity minus infinity is indeterminate, and furthermore, it's not one of L'Hopital's indeterminate forms, which makes us a little sad. It means we have more work to do here. So the work to do is, let's go ahead and try to rewrite this limit as the limit as x approaches 0 from the right, and then let's get a common denominator with this original expression. So I'm going to write it as x times tangent inverse of x. That would be just multiplying these two original denominator terms together for an LCD there. And then, of course, to adjust the numerators, that would give me tangent inverse of x for the first numerator minus x for the second numerator. And at this point, if I try plugging in 0 for direct substitution, this is going to give me, in the numerator, tangent inverse of x as x approaches 0 is 0. We already determined that. Minus 0, of course, that's 0. All over. Down below, we have 0 times 0. Okay, so the point is we're getting 0 over 0 now for the indeterminate form, which is actually good news. That's one of L'Hopital's indeterminate forms. To use L'Hopital's rule now, which is where we're going, we want to take the derivative of the numerator and denominator, but really only in this most previous step that we've done here. So if we look at that original numerator, let's rewrite this as the limit. We haven't finished with the limit yet. We have to keep rewriting that until we actually take it. We have the limit as x approaches 0 from the right of, now in the numerator, those terms were tangent inverse of x minus x. Well, the derivative of tan inverse, as you may recall, is 1 over 1 plus x squared. Okay, that's one of our inverse trig derivatives. Minus the derivative of x would just be 1. And then if we go down below, in the denominator, we have a product, which means we're going to have to use the product rule. So we'll say first, which is x, times the derivative of the second, which would be the 1 over 1 plus x squared showing up again, plus the second, which is tan inverse of x, times the derivative of the first, which is just 1. But now we have this fairly ugly looking complex fraction, so let's go ahead and just simplify that right away by multiplying. I'm going to multiply the major numerator and the major denominator, each by this 1 plus x squared. That will just help simplify the complex fraction. Of course, that's not the only way to simplify the complex fraction, but it's a good way. If we do this, we'll end up with the limit as x approaches 0 from the right. If I distribute this 1 plus x squared into all these terms, I'll end up with 1 minus, and then 1 minus x squared. Be careful on the signs of that. Really, it'd be the plus, but in parentheses, this negative would be distributed over, and it'd really then be a minus. So 1 minus x squared in the numerator. In the denominator, we'll end up with x plus tangent inverse of x times 1 plus x squared. If we try direct substitution now, after finally using L'Hopital's rule here, let's see what happens. In the numerator, when I plug in 0, I'll end up with 0. In the denominator, when I plug in 0, I'll get 0 plus, we've already discussed tangent inverse of 0. It's 0, and then 0 times 1 would still be 0. So interestingly, we got 0 over 0, but that's still indeterminate, which means we're going to try L'Hopital's rule again. Yes, sometimes you actually have to use L'Hopital's rule multiple times, and it can work just that way. So we're going to now say, according to L'Hopital's rule, and of course we're doing this next phase of L'Hopital's rule from the most recent previous step we had just done where we had already taken the derivative. So now we're taking the derivative of those derivative pieces. So I'm going to say limit as x approaches 0 from the right, and then in the numerator we're taking the derivative of this previous numerator, which really was just negative x squared, so that'd be a negative 2x. And in the denominator, the derivative of the x was just a 1. So we'll say 1 plus, and then for this second term, it's a big ugly product, which means we're going to need the product rule. So we'll say first, which is tan inverse of x times derivative of the second, which would be a 2x. So first times d second plus second, which is the 1 plus x squared times derivative of the first, which would be 1 over 1 plus x squared. That's actually kind of good there. Those will cancel. In fact, let's just strike those out right now. So we have first d second plus second d first, and that's the product rule happening as part of the derivative here of this denominator from the previous step. We're working on our L'Hopital round 2 here. Continuing with what's left here, we have the limit as x approaches 0 from the right of negative 2 over, and the denominator, if we just clean it up a little bit, we really just have 1 plus, actually we could even say 2 plus 2x tan inverse of x. Okay, so now we can try direct sub again. Oops, I forgot the x up there in the numerator. It's negative 2x in the numerator over the denominator of 2 plus 2x times tan inverse of x. If I plug in x as 0 now, we'll get 0 above, and down below, tan inverse of 0 is 0, so really it's 2 plus 0 down there, which means we really have 0 over 2, which is actually 0, which is good news. That means we have a limit. Okay, let's do one more example. I know this has been a lot, but this is probably one of the most important examples here at the end. For this sixth example, we're going to find the limit as x approaches 0 from the right of tangent of 2x all to the x power. Now, we can try direct sub right away just to kind of see what we're working with. When you plug in 0 for tangent of 2x, tangent of 0 is 0. And so we really have 0 to the power of 0 when doing direct substitution right away, which is actually bad news. That makes us sad because that's not one of L'Hopital's rules. Furthermore, there's not a real clear way to go around with any other method we have. We're going to try a bit of a trick on this one that actually will bring back something we did in the past using logarithms. But let's start by saying this. Let's go ahead and let y equal tangent of 2x all to the x. So that's just the original expression we were giving here. We're just going to set y equal to that for a second for convenience here. Then we're going to take the natural log of both sides of this equation. Now you may be saying, well, why are we doing that? I wouldn't have thought of that. Okay, well, notice this x in the exponent here. That might be the motivation to try to do something with it, and really the only good way we have to do something with a power up like that is to use a logarithm and then throw it way down in front, as we've seen before with logarithms. So that's kind of where we're going with this. We're going to now rewrite this as the natural log of y equals, and then I'll say x. I can throw that x down in front. It'll be x times the natural log of the tangent of 2x. That's just using logarithms there in algebra. There's really no calculus happening quite yet. Now, we ultimately want to take a limit here. So notice what's happening. This original expression that we set, we have tangent 2x to the x. That's what we set y equal to, which means I'm really trying to take the limit as x approaches 0 of this y value. So what we're going to do is introduce a limit into our problem where it stands now. So I'm going to take the limit as x approaches 0 from the right of the natural log of y, the left side of this equation. Of course, that should equal the limit as x approaches 0 from the right of the right side of our equation, which is just the x ln of tangent of 2x. And this, of course, the right side of this could be done with direct substitution, but you'll end up with 0 times. Now, this piece, natural log of the tangent of 2x. Okay, so we've done a bit of work with some of these functions already in the past. When you plug in 0 from the right of tangent of 2x, that's approaching, like if you take a quick look at the graph of tangent, you may recall it has a couple of vertical asymptotes and then it snakes to the origin in this way. So as you approach 0 from the right, you're approaching 0 from positive values in the tangent function, which means you're approaching 0 from the right for natural log, which means you're approaching, if you consider that function, there's no room over here. So that function plummets down toward a vertical asymptote. For the natural log, which means ultimately we have 0 times negative infinity for this limit. Okay, now that's kind of tying a lot of things together, but the point is that's actually kind of bad news because that's not one of our happy L'Hopital indeterminate forms. So we're going to have to pull another trick on this one. Let's go ahead and rewrite. We have the limit as x approaches 0 from the right. On the left side of our equation, we're going to keep this ln of y over there for the time being. And we'll set it equal to, on the right side, here's where we're going to throw in our trick. We still have the limit as x approaches 0 from the right, But this is where we have our indeterminate problem. And we would love at least to make it a L'Hopital indeterminate form. And we can do so in the following way. We're going to take this expression that was in the brackets, and I'm going to take this x that was in front, that factor in front, and do a little flip with it. So I'm going to keep the natural log of tangent of 2x, kind of where it is in the numerator, but instead of writing x multiplied in front of it, I'm going to write 1 over x underneath it, which algebraically is equivalent. You could flip this 1 over x up and over, and it would be ultimately multiplying the x times the natural log there. So we'll leave it like that, which conveniently now will convert this into be an infinity over infinity, which is actually good news because that's a L'Hopital indeterminate form. As we're doing these limits within these problems, there's also often nested limits. It may be necessary to go back and review other things with limits we've done already. For instance, if you couldn't quite catch why this was infinity over infinity, there may be some need for deduction with this denominator 1 over x and things. Go back and review as needed, but for now we're just going to go with it. This is infinity over infinity. So let's go ahead and be happy that that's a L'Hopital form, and then rewrite. We have the limit as x approaches 0 from the right. We still have ln of y on the left side, but now on the right side, this is where we're going to be taking L'Hopital's rule, so we do derivatives here, which means we have the limit as x approaches 0 from the right of, and then notice this numerator, it was natural log of tangent of 2x. Okay, so the derivative of that would be 1 over it, so 1 over tangent of 2x, but then chain rule here, so 1 over tan 2x times the derivative of the tangent of 2x, which would be secant squared of 2x times 2. There's another chain popping out even there. Okay, so lots of derivatives happening there. Down below with the 1 over x, the derivative of that would be negative 1 over x squared, which means we've now at least taken our derivatives. Let's see if this is going to help us at all. If I keep this going, I have the limit as x approaches 0 from the right. And then let's convert these trig expressions to some more basic ones. 1 over tangent is really cotangent, which means we really have cosine of 2x over the sine of 2x for this 1 over tangent of 2x there, times, and then secant squared of 2x, that's really 1 over cosine squared of 2x, and then of course that was times 2. Of course this is all still over negative 1 over x squared. But then if we simplify by taking this negative 1 over x squared and kind of flipping it up and putting it upstairs with all the other stuff, then we would end up with the limit as x approaches 0 from the right of negative 2x squared. So that's the combination of this factor of 2 at the end and this negative 1 over x squared flipping up and over. So we have negative 2x squared over sine of 2x times cosine of 2x. I'll get rid of one of the parentheses here, there's a little too much going on. And that's because, of course, one of these cosines would cancel with one of these below, or the cosine in the numerator would cancel with that other squared below, giving us only one of them. So ultimately we have this. Now this isn't a whole lot better, but let's rewrite this yet again. This is the limit as x approaches 0 from the right. If I split this up, it actually gets interesting. This is 2x over the sine of 2x times negative x over cosine of 2x, which means we actually have lurking here in this first term, this first factor, the 2x over sine of 2x, a special limit. You may say, well, what's going on? I thought that's reversed. Wasn't it sine of 2x over 2x? Well, yes, but you can do some kung fu with the original special limit. The original special limit had sine of x over x, but that's really equivalent to 1 over x over sine of x. And so you can kind of find your way back through all of this to get to this special limit and know that it still does work to give us the value of 1. Of course, this is all still times this second term, which would be 0 when we plug in x as 0, which means ultimately we have 1 times 0, which is 0. Okay, now, this is where this problem gets interesting. We're not actually done with the problem, because if we try to piece together what we've been doing here, we have 0, but let's remember where this all came from. What we can now say on the left side of this equation, which we just kind of stopped recopying here, we could rewrite that and say the limit as x approaches 0 from the right of the natural log of y, which is the left side of this equation we had here originally, that now equals 0, which we kind of found as the limit to the right side. Well, we ultimately want to find the limit of just y. Remember, we called our original expression just y. So we can find the limit of y, we're good, and we nearly have it here. If we raise both sides of this equation to be the power of e, just kind of exponentiating both sides, that kind of just goes back to some rules with exponential equations from algebra. Then, so we can do this. We can raise both sides as a power of e. Okay, then we end up getting the limit as x approaches 0 of e to the ln cancels, giving us just y. And on the right side, e to the 0 is 1. And ultimately, 1 is it, because we remember we called our original expression y, and we've ended up now using just y and saying the limit of y as x approaches 0 from the right is 1. So this is a fairly complex example, but it does tie together a lot of really key things, and it's good to practice more like this. Probably read through this a few times. Hopefully it's helpful.